So the basic algorithm is the CPU will produce an address, and we'll have this cache, which we're representing here as a table. And the table contains both information about which addresses are stored in the cache, and then the actual memory contents of those addresses. So the cache knows two things. It knows which addresses it has, and it has the contents of those addresses. That makes sort of sense? And so the CPU, when I ask for a particular address, will look through the cache, will search the cache, and we'll talk about how that's done in just a second, to see if I ask for memory address A, oh, it says I've got that, and it will respond. If I'm writing to memory location A, it will say, fine, I have that in my cache. You're telling me a new value for it, so I'll just update the cache. And the processor, can continue on, and then the cache itself will worry about updating main memory with that new value. If there's a miss, what does it mean to miss? I ask for C, address C, and it's not in this table. Hopefully that doesn't happen very often, but when it does happen, I have to go off and pick some line of the cache, that thing in the refrigerator I'm going to throw away, the sentient thing apparently. The thing in the refrigerator I'm going to throw away, and I'm going to then replace it with the contents of memory location C. So the first time I ask for C, I have to go off and fetch it from memory. That's okay. I mean, it's the only choice I have. It's slow, and the CPU is drumming its fingers, saying, I'm still waiting for C. It doesn't have much to do. I'll talk more about that next time, actually. The whole notion of hyperthreading is Intel's answer to what happens if the CPU doesn't have much to do. Maybe it could go work on some other program while it's waiting, for some number of cycles for the main memory to get back with the answer to your cache miss. Okay, so I have to pick a replacement and go off to the main memory and bring it in, and I'm going to put it in the cache in the hopes that you'll ask for it again. And statistically, we hope that will be true, and that's how I hope that, in fact, the hit rate will be reasonably high. Okay, and if we believe this diagram about locality of reference, the answer is once I get all the elements of my working set into the cache, you will keep asking about them again and again and again. The same parts of the stack frame, the same instructions from memory. And so once I put it into the cache, having made an investment to put it there, then I'll take advantage of it being there again and again. So how do we search the cache? Well, the most obvious thing to do is to have an office full of Clark Kents outside my office door, each of whom has a piece of paper, in the hopes that somewhere in that stack of information, I'm going to do this sort of parallel search. Right? So what I'm going to do is to ask all of this team out here to say, okay, find me bit diddle, and they're each going to look at their piece of paper in parallel, right, and sort of go, aha, I've got it, and the other guy's saying, no, not me, but one guy has it. Alrighty, so this notion of sort of the best type of search we can do is to look at every row of my cache, every line of my cache, to see if, and I'm asking for a particular address, to see if that particular cache line has the address, and I'll look at all the lines in parallel. So I'm going to design a piece of hardware where I'm going to use these registers here to hold both the data itself and something we call a tag. What's the tag in our cache? What information do we need in order to find a piece of data? We need its address. Right? So I call a tag here, because that's the sort of jargon name that we give the indexing field of a cache. And we know that to mean the memory address. The CPU is asking for an incoming address, so each of these tag fields holds an address, and the associated data register is holding the contents of the memory location that has that address. So I'm going to build hardware comparator, using XOR gates and OR gates and AND gates to basically compare each bit of the address with the corresponding bit in the tag, and if they all match, I'm going to say, I've got it. And one of these lines will respond, and if it does, I get a hit back to the processor, and I put the appropriate data onto the lines. Everybody happy with that? So a fully associative cache. Look at the ratio of the hardware to the actual data storage, right? So we have a register holding the various data words, but we have to hold that big address, which is as big as the data in the case of a beta. We have this comparator circuit. We have all this routing circuitry we have to put in. These are very expensive. Right? These fully associative caches are very expensive. We will find occasions to use them, but in terms of, they're very, very good. If we have it in the cache at all, we'll be able to find it quickly just in the cost of this small piece of combinational logic to do the comparison. So in orders of picoseconds, I'll be able to say, I've got it, but I have to spend a lot of hardware to get there. So it's inexpensive. Is there a cheaper alternative?